Okay, so let's do 5.5 exponential and logarithmic equations. So I'm just going to do just a bunch of problems. There's kind of, um, all these examples are a little different, and so the strategies are all a little bit different. So uh, so one thing that the book just says that as a principle is that if you have an exponential equation with this, and then both sides have the same base, and it's just b to the x is equal to b to the y or something like that, then it automatically follows that that's equivalent to just saying that the exponents are equal to each other. So that's the same thing as taking log base 4 of both sides. But that just, so either by taking log base 4 of both sides, or I believe they call this like the principle of equal exponents or something like that. But if it's 4 to the a is equal to 4 to the b, then that just means that a is equal to b, and that's an if and only if, because you can take log base 4 to go from this to line 2 to line 3, and then you can take 4 to this power is equal to 4 to that power to go right back to saying that this one, if one is true, the other one is true, and vice versa. So this one ends up being, so this is kind of like taking a logarithm is what that step is, but you don't necessarily have to think of it that way. Other problems are harder, and maybe you really do have to take a logarithm. But for this one, it's just sort of principle of equal exponents, or equal bases or something. So whatever the book calls it. I know the book gives it a name. I just base exponent property. I think there's one test problem where it asks you by name to appeal to this principle. It's just a fancy name for something that sort of comes kind of naturally. If the bases are the same and then you have an equality, then it means that the exponents are the same, and vice versa. If these are the same, something to this power must also be equal to something to that power. Okay. Let's do something a little more tricky. Well, actually, significantly more tricky. This one is kind of weird, but sometimes you'll see ones like this. This one is actually solvable. It's just not immediately. It's not immediately obvious at all, why this should be possible. But to see why though, let's take ln of both sides. And what happens? Well, we have an exponent which comes outside. That's the natural log of m to the p is equal to p times log of m. That's the identity there. And the idea is that we have a variable x and everything else is just constants. So it's kind of, we have we wanted to x plus constant times constant, because ln of 5, well, it's some number, it's 1 point something, and then 1 minus x times ln of 4. So if this were like 2x, you would know what to do. You would just combine the x's, and you can do that. It's just the constants themselves are a little bit ugly. So 1 times ln of 4 and then this is negative ln of 4 times, not strictly necessary, but it looks nice because, you know, if it's blue, then that x, we have, how many x's do we have? We have negative ln of 4 x's on the right hand side, and we have positive ln of 5 x's on the right hand side. So those are like terms. And these are just two constants. So subtract the twice ln of 5. And we add x times ln of 4. So we add so how many x's do we have? We have x times, and this is, if this were 2 and 5, you would have 7 ln of 4, but we don't have exactly that. We've got, or 7x, sorry. We have, this is how many x's we have. We have ln of 5 plus ln of 4, which is going to be like probably 2 point something is how many x's we have, and that is equal to some other number, which is ln of 4. Looks like the right hand side is it's probably going to be negative. And so it's x times a constant is equal to some other constant. So if this were 3x were equal to 5, you would just have x is 5/3, but not quite so simple. And this one is actually in the book, and the book printed an answer. I guess I could double check this, but you have to be very careful about parentheses. You have like ln, you have parentheses, opening and closed, but you also have to have the entire numerator and the entire denominator also have parentheses of their own. And you should get negative 0.6. The book does it to the nearest 1,000th. So that's, let me see if that's what I get. So you open a big parentheses. You need to do ln of 4, and then subtract twice ln of 5. And then you divide that whole thing by ln of 5 plus ln of 4. This had better be that. Yes, I'm getting exactly that. So I'm getting 0.61173 something or other, and so to the nearest 1,000th, you get exactly this. All right. So that one's a little tricky, but if you see it, you know how to do it. It's if it looks like different bases, but it's just base to some linear expression with x on both sides. Well, you could have done log base 10, and then all of these would be log base 10s, and then you would get exactly the same answer as long as you're consistent. But I chose natural log. It's slightly shorter to write on the dry erase board. So I just did ln. You have the identity, and then you collect like terms. So everything that you distribute, this is a constant times constant plus constant x. Collect all of the x times whatever, factor out the constant, divide by the constant. And it's a little bit of a handful. There's several things to keep track of very carefully, but you can do it. It's quite doable. Just a little bit of work. And yeah, there are a lot of distractions, but once you see, what is it that I'm looking for, there's a nice pattern. It's just also a lot of distractions that are hard to see fast, but that's how you do it. Here's one that's a little more typical, and I'll call this number 3. The book likes to omit parentheses and whenever there's something immediately after. Like when you get to a plus sign, it's implied that the parentheses have ended. So the implied parentheses are right here. So if they write a plus or a minus, but they didn't write any parentheses at all, then it's sort of implied that that's where their parentheses are. And then they actually write down this because they want to say that I'm actually not taking just log of x this time, I'm taking log of x minus 9, which is a totally different thing. And this whole thing is equal to 1. Okay, so there are a couple ways you could do this. If you don't like, it depends on there's 2 ways you could go about it. I'm going to go solution 1, solution 2, but eventually they're both going to have exactly the same thing at step 3 or something like that. So if I don't like logarithms very much, if I just want to get rid of the logarithms, then I just say 10 to so every time that you do something with a log identity, you could have done the same thing as you could have done the same thing with an exponential identity. Whenever you're just shuffling things around, well, 10 to the a plus b is 10 to the a times, so it's 10 to this power times 10 to that power. Well, you still have to do, you don't get anything for free, really. It's like you still have to know some kind of identity very well to get to the answer. So that's if I want to think about it, if I want to do, if I'm really confident about my exponential identities and that's how I want to do it, that's how I do it. So the other way of doing it is before I do any 10 to the whatever, well, I just learned this yesterday, so maybe I feel good about it. Maybe I'm already feeling pretty good about this. Those are 2 logs with the same base. So log of m plus log of n is equal to log of m times n. So you get, and now that I did an identity there, but I still need to do 10 to this power on both sides. So 10 to the first is 1, and then on the left-hand side, again, it's x times x minus 9, and no matter what I did, solution 1 and solution 2, eventually we get to the same. It really boils down to this problem here. So x squared minus 9x minus 10 is equal to 0. And the problem is well, for this kind of problem in particular, you can wait until the very end to check your answers, and that's equivalent to checking the domain of all the functions in the original expression. So the very first thing that you had was log of x plus log of x minus 9. Well, oh no, I have to take log of minus 1. If you plug that in your calculator, you'll get an error because logarithms, their domain is strictly positive, not including 0. You have to take log of a positive number, or else everything is broken. So that's no good. So log of, it says that log of minus 1 plus log of minus 10 is equal to 1. Well, that's no good. Because the actual equation itself is this one. This equation was almost equivalent, but not quite. It's just the original expression is undefined. You can't simplify it. It's just undefined. But the rest of the time you get this one, which is defined. So that says that log of 10 plus log of 1 is equal to 1. Well, let's see. That's log base 10 of 10 to the first. And that's 10 to the 0th. So log base 10 of 10 to the first, you get 1 plus 1 is the exponent on 10. 0 is the exponent on 10 here. So log of 1 is 0. That's the one that feels weird, takes some getting used to, but it's actually correct. So that's it. That's your solution set. Yep. Okay, so that's about all I wanted to say about that one. Sort of a mixed bag of whatever. Let's do one more. Where did I put everything? There it is. Okay. This will be number 4. I'll call it, yeah. So some of the most straightforward applications are the ones that are most kind of the biggest motivation behind logarithms in the first place, perhaps, is stuff like this. It's like, you've got exponential growth. How long does it take to turn 100 of something into 500 of something if you've got exponential growth? So that's, that's pretty typical. And again, you could take logarithms of both sides and then use the log identities, but there's no reason that you have to do that. You could, the most reasonable thing would probably be to just divide by 100 as your very first step. And now you can take ln of both sides, because that's what ln is actually kind of, that's the whole point of natural log, I guess. So big parentheses like that, and then that divided by 0.3. I got 5.36. I guess the book would have given more decimal places, so let me do that. Okay, so that's to the nearest 1,000th. That's what you'll get. Alright, so let me just double check. That was kind of, there are a couple that were a little bit harder, but kind of not necessary. I think we're kind of skipping the harder ones, or, well, one of those was a little bit hard, actually, yeah. But, okay, what have we got? Okay, I kind of like this one here. So yeah, let's just do one more algebra thing. So log base 8. We haven't done those other bases as much lately. So we've got that minus log base 8 of x is equal to 2. All right, so I'm going to go ahead and I don't know, I find it smaller. It's like I could have taken 8 to both sides and used exponent identities, but somehow I don't want to write log 8 like multiple times. It's just less writing if I just combine the logarithms. It's but either way, you want to take 8 to, you want to exponentiate both sides as 8 to that power. So 8 to the second is equal to 8 to either this whole expression here, and then use exponential identities, or this one is better because this step is easier if it's just a single log base 8 of something. So so this one's kind of interesting. It looks just like the other one, except it was minus instead of plus, but somehow a lot of things are just very different, because minus instead of plus at this step means that now you've got divided by x instead of times x. So it's not a quadratic, it's actually linear divided by linear is equal to something. So you multiply the denominator. Now the whole thing is just linear. So logarithms can be a little bit deceptive like that. This same problem with a minus instead of a plus, it's just night and day. It would be, if there were a plus here, you would have a quadratic equation, and then who knows what, you'd have lots of stuff, and you would have to solve it, and you'd get an answer at the end. But it just, that little tiny minus sign makes a huge difference. It just sort of flips the entire, flips a lot of things around. So it can be, logarithms and exponentials, it's like you're transforming your whole world, and everything is kind of different. But how do you handle it? Well, you use your identities, group things, and then cancel stuff out to solve for x. And then does this end up working? Well, you'd have to use like a calculator and the change of base formula, because individually, this is going to be some decimal. This is going to be some other decimal, and it should, you could do it, but if you wanted to check your answer, you would have to use the change of base formula. So, but you should at least check that this is like the only issue is the domain issue. So we're trying to take log of x plus 1, and we're trying to take log of x. And if you can't take log of 0, you can't take log of a negative. So they are defined, which means they're not undefined, which means this is not an extraneous solution. So if you wanted to be super duper careful about it, you could so let's go ahead and do it. Let's see what happens. So we get, let's use the change of base formula. So it's ln of 1 plus 1/63 divided by ln of 8 minus ln of 1/63 divided by ln of 8. And is this equal to 2? Question mark, that's what's supposed to happen. Calculator, I put it somewhere. There it is. So I'm going to keep this minus right here, and I'm going to compute the other part of that in my calculator. So this is what I'm getting. So ln of 1/63 divided by ln of 8. 3, 4, 5. 1, 2, 3, 4, 5. Yeah. All right, so this negative here, and then there's a double negative. That's the way I put it in my calculator anyway. I just put this part in my calculator and kept this minus on the sheet of paper separately. And that will do it. The change of base formula. So checking your answers for these log problems, yeah, sometimes it's a nice round number and you just check it, but other times, if you really, really wanted to check your answer, well, that's a whole new problem because you have to do the change of base formula to actually compute log base 8. But you can do it, and that's how you do it if you really want to. It's a nice exercise. And yeah, I think just one more problem. I think I thought maybe I saw one like this on the MyLab test. I was feeling a little bit paranoid, so let's include it just so it doesn't come up later. And this will be the very last one. I'm gonna okay, so we've got problem. Yeah, okay. I'm just write down the solution so I don't have to look at the paper later. There are two solutions. It's to the nearest 1,000. There's, it's not obvious at all that that's the solution, but let's see how we do it. Well, I'm going to multiply both sides by e to the x because it's like this is e to the x and this is 1 over e to the x. But I kind of don't want denominators. I kind of want everything to be e to the x or e to the x squared, or just a constant. So what I get here is if I multiply these two, I get e to the 2x, which is like e to the x squared. It might even be nicer to think of it that way. The whole point is it's kind of like a quadratic, but e to the x times e to the minus x is just 1, because it's you add the exponents as e to the 0, which is 1, or you just think of it as a number times its reciprocal, and then 5 e to the x. So it's like e to the x is the variable, and we've got quadratic, but it's not x, it's e to the x every place that we need to have x. So it's a quadratic, but the variable, let me just, I don't know, I'll put it in red. So this red e to the x, if I thought of that as like capital X, it'd be 1x capital X squared minus 5 capital X plus 1 is equal to 0. It looks like a quadratic, but what we end up having here is that e to the x is equal to, well, there, e to the x, it's squared first power plus constant. So we got quadratic formula, negative b plus or minus the square root of b squared minus 4, a is 1, c is 1, all over 2 times a. Yeah, so variable is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Pop goes the weasel is the song you can sing to that. And all right, so we get 5 plus the square root, plus or minus the square root of, that's 25 minus 4 all over 2. 5 plus or minus the square root of 21 all over 2. And the whole point is that's not x, but that's e to the x. So we have to do one step farther. So to get x, we have to take ln to cancel out the exponential function. And that's where you get the positive 1.567. That's solution 1, and then the other one is going to be from here. So x is ln of e to the x, which is ln of, sometimes I write the script L, sometimes I don't. It's just a style thing. And so that's kind of interesting. The final, so the solution you get at the end, is that a coincidence? It's not quite a coincidence. It's something in hindsight, it actually kind of makes sense. If I plug in a positive number here, then e to the minus x is e to the x, and e to the minus x is going to be e to the, one of these is going to be e to the 1.567, and the other one's going to be e to the negative 1.567, which is, pretty interesting. It's like, these two are they're like twins, and it's just which one is which. If you switch the plus and the minus, then it's just these two get switched. That's kind of interesting, but anyways, that's kind of how you do it. That's so yeah, we're almost there. The only thing left is some sort of word problem kind of stuff, and for specific word problems like compound interest and exponential growth and decay, some of these things have names, and they have like labels that are kind of standard, and we'll just get a little bit used to that notation, and that'll be like the very last thing for the whole course. So it's a pretty big chapter, but if you made it this far, you're in the home stretch. You're almost there. So hope it's going well. Hope you're hanging in there.